Video explains using an advanced control system. The controller used is an advanced cascade controller with kinematic feed-forward, PID trim, and disturbance observer compensation. The outer loop is proportional only, so when the drone is far from the target, it commands a larger velocity limited by saturation. Near the target, a bounded PID trim improves convergence, reduces steady-state error, and adds damping. Integral saturation and leakage reduce windup, especially after target changes. When wind is enabled, the disturbance observer builds a compensation term from persistent error. Yaw is controlled separately using another PID loop. The main tuning difficulty was balancing speed and overshoot. High proportional gain improved response time, but too much of it caused oscillation, so the final gains were optimized to give fast convergence without overshoot. This video shows the flight of the simulation drone using our controller. In wind disabled configuration, the position error mean, position error standard deviation, and yaw error mean reach below 0.01, and yaw error standard deviation reaches below 0.001 in the required time frame of 10 plus 10 seconds. When wind is enabled, these parameters converge but do not meet the desired values on time. These plots show the desired values and the actual values of the position and yaw error parameters. Position error mean converges to about 0.0045. The standard deviation of the position error converges to 0.003. The second diagram shows that yaw error mean is negligible compared to the desired value, while the yaw standard deviation converges to a value lower than 0.001. This slide shows the real flight of the drone when the controller is applied. In the first scenario, the drone is set to move at 30 centimeters per second. It follows a gentle trajectory with no noticeable overshoots. A similar control trajectory is shown by the 60 centimeters per second speed setting. In both cases, the drone lands safely at the target location. In the 80 centimeters per second scenario, the control is struggling to meet the set points and overshoots across the arena, and it does not land safely. This plot shows the position error mean and error standard deviation for the speed settings. The least position error mean is for the 60 setting, while the highest is for the 80 setting. Standard deviation is least for the 30 setting, whereas it is highest for the 60 setting. The yaw error results show the 30 setting yaw error mean is twice as high as that at 60 setting. The lowest value is for the 80 setting. Yaw error standard deviation is also least for the 80 setting case. We have designed a controller that works perfectly in simulation. Position and yaw error parameters converge to the desired values within the time limit. When the controller was used on the drone successfully navigated through the targets and landed safely at speeds of up to 60 centimeters per second. Position and yaw error parameters converge, but the values they converge to are larger than the ones seen in the simulation. It should be noted that more operation time is taken by the drone compared to the simulation. Possible reasons include vibration. The chassis of the drone may vibrate, or the battery could be sliding, causing stabilization problems. Lower battery charge can cause the rotors to turn slowly. Intensive signal processing introduces latency. Real world contains noise, so the sensor data that's used is not ideal, and this can also influence the controller. I hope this video was informative to explain the implementation of our Cascade PID controller. Thank you for listening.